Okay. So the trick how to make this work more generally is actually quite nifty, and this is probably the most beautiful part of that sketching paper. So they come up with an algorithm as follows. They take the data stream and at a random point uniformly over the sequence of the data stream, and I'll get to that in a moment how you can actually do this. They pick a symbol, let's say A. And then from there on, they start counting how many times that symbol occurs. Let's say here it occurs 3 times. And let's say for another random variable, well, we start here, and we start counting C, and it only occurs once overall. And then I'm going to multiply that by the overall length of the sequence times number of counts that I have so far, r to the k, minus r minus 1 to the k. And this looks like an entirely bizarre random variable to make any sense whatsoever. I find it highly counterintuitive. Until you see this. Here's why it actually works out to be the mean. So basically, let's just for the moment pick a single symbol, let's say x, and what happens throughout the sequence is with equal probability I'm going to pick the first, the second, the third up to the nx occurrence of that symbol. So I get with equal probabilities 1 to the k minus 0 to the k plus 2 to the k minus 1. Here they are, up to the n1 to the k minus n1 minus 1 to the k. They get that for the second symbol and the third and so on up to the last symbol. Now if you squint at that hard enough, you'll see that everything disappears but n1 to the k. So there's some telescopes. This guy cancels with this guy cancels with that, and so on and so on. So this is how you can see this actually gives you exactly fk. Now to get the variance, it's a lot of brute force algebra in order to get this exponent. It's quite surprising. Now the nice thing is that this immediately implies that that's the number of bits that you will need for estimating fk. So the interesting dependence here is on essentially the number of distinct symbols raised to the power of 1 minus 1 over k. Before that, we saw a case where this didn't really even occur, and was for f0. Now, the lower bound is actually a bit non-trivial to prove, so they use a few tricks from communication theory to get the lower bound. But what it really means is that for any fk with k greater than 2, you're pretty much screwed. You're going to need something that will require a substantial fraction of the total number of distinct symbols in terms of as storage. So in other words, if you want to get k greater than 2, you're probably going to be almost better off using an algorithm that just has a simple lookup table where it looks at the occurrence of each of those symbols and just counts how many times they occur. And if you do that, you get a Gödel prize. It's one of those really amazing papers. So if that all looked a little bit too complicated, well, let's see how we can actually do nice uniform sampling of individual symbols from a string. Actually, I should probably before that briefly explain how you can pick a random element from a string. Because I don't know how long the string is, and I want to be able to get a random element at any time. So reservoir sampling does that, for instance. So let's say I just want to get one element. The first element that I'm going to see, I'm going to pick. Okay, so it goes in here. Now a second element comes along. If I want to make sure that I pick the second one with now probability 1/2, all I need to do is with probability 1/2, I'm going to throw away what I had and pick a new guy. Now the first and the second one occur with equal probability. The third one comes in. The third one now needs to be picked with probability 1/3. If I pick it with probability 1/3, and knowing that the other two are with equal probability picked, everything will be picked with 1/3. So I just pick this guy with 1/3, and I keep on going, and I pick the nth guy with probability 1/n. This gives me a random element from the stream. The amount of work that I have to do in order to get this, as in the number of instances that I'll have to pick in this way, is order log n. You can work that out easily by just summing over things. If you sum over the probabilities, and that gives you log n, essentially. It's upper bounded by log n plus 1. Okay. So that's how you go about this. Now, in some cases, you might not just want to pick a random symbol in the stream, as in a random position, but a symbol with a random identity. So that's a different problem, right? So I might not just say, well, I want to find out which symbol occurs at position 20, but I want to get a random symbol regardless of the free probability of its occurrence. Now, if I know the entire domain beforehand, it's very easy. I just pick a random guy from that set, and then I just keep on watching out for it. Now, since I don't know what my set is, well, here's the algorithm. It's actually very beautiful. So I go and initialize my counter with 0 and some auxiliary variable g to be infinity. So then you go and observe some x from the stream, and I compute the hash. If the hash of the symbol, and I'm assuming I'm not getting any collisions, so I'm just sort of ignoring that entirely. If the hash of x equals g, I increment the counter. If hash of x is less than g, I reset the counter to 1 and set g to be hash of x. Okay, so what's going on here? So clearly, if at some point I pick the symbol and then I see it again, okay, this condition will trigger. So incrementing the counter is fine. Now, remember what we did for consistent hashing when we assigned keys to machines. We picked the machine with smallest hash. And that gave us a uniform distribution over machines. Here we get a uniform distribution over keys for the one key that will be the one with the smallest hash. And that's exactly the one that I want to get. And with this procedure, I will be able to find its count. Now, there's a lot of extensions that you can do with that. For instance, you could pick the k smallest guys. And this is a very famous procedure, so those of you who might have worked for an internet company would have heard of shingling. So Andre Broder, for instance, was one of the people who invented that. He just picked the k smallest guys, the item with the k smallest hashes, and this will give you a good fingerprint of a document. Then you can do document comparison by just checking whether those two lists are similar. You can do set intersection and all sorts of interesting things with it. If you then say, well, actually I don't only care about the identities and the counts associated with the smallest items, but I care about what the actual hash value was, then I can do something even better. So this is an algorithm by Lee, Hasty, and Church. And essentially, if you think about it, if I perform this hash, and I end up with a very small number for my hash function, then it means I must have seen a lot of symbols. That's exactly the Flageolet-Martin argument, right? And that's what basically this trick is using in order to get better estimates for inner products. So Ping Li has written probably about half a dozen very nice papers on that very issue. Okay, now we're going to move on to a different algorithms family, which are a lot more discrete rather than averaging based. Okay, here we get those. So And it's an amazingly simple algorithm, but it's actually very effective. And you can even prove that it's optimal. So suppose I have a data stream and I want to find the k heaviest items for an arbitrary sequence. And furthermore, I want the algorithm to be so that if my distribution is Paolo distributed or has other nice properties, that I can automatically exploit it. And I would like to use order k space and get order 1 over k accuracy in some cases. So why would you care about it? Well, for instance, in advertising, you might want to find the most frequent customers that you have. You care about it for two reasons. First of all, you want to send the most frequent customers even more ads, such that they click on even more stuff, so that you make even more money. Secondly, you worry about the guys where you have an unreasonably high number of clicks. Because those are probably people who are gaming the system and, essentially doing click spam. Why would you want to do click spam? Let's say I have a flower shop, you have a flower shop, and we both advertise. And I really want to make sure that I'm winning all the auctions. And I'm going to pay some people in essentially some country where the salaries are very low to click on your ads. Each time an ad gets clicked, you pay money. Your budget gets exhausted for ads, and once this is gone, I'm the only one who's advertising for flowers, and I win all the auctions from real customers. That's obviously not something you really want, and so this is why you want to find the guys who get a lot of clicks at some point. There are fancier mechanisms to detect it, so don't worry, it's not that easy to cheat. Now, as said in advertising, you also want to find popular keywords in use, so you want to basically get trending keywords. The web search, you want to get the popular queries very quickly, and you want to detect attacks. So in, just intrusion detection, an obvious thing you want to do is you want to find out whether you're getting a lot of requests from some IP numbers. Of course, you can actually safeguard against that. Let's say you have basically a large botnet of 1 million machines, then each of those machines is going to send, one request, and if you coordinate it right, then, those frequency-based intrusion detectors aren't going to be very lucky. But at least you can safeguard yourself against the slightly less inspired attacks. So, here's a simple algorithm. I take a table of k counts and corresponding labels, and I initialize it to be empty. So, now, I observe an instance, and if this instance is in the corresponding label set of my data structure, then I go and increment the counter by 1. So far, so good. We already know that the word dog occurred 20 times. The dog comes along once again, it goes up to 21. Fine. Now, let's say the word cat comes along and there is no cat in our data structure. Well, then we pick the smallest item in our data structure with the smallest count, let's say mouse, and we throw out the mouse and rename it into cat and increment its count. So, there you go. This is our initial data structure, and we observe E. Now E is not in our data structure. We take D. I could have picked C as well, but for better or worse I picked D. And I go and increment its count by 1 and rename it. B comes along. Well, we already have B in our data structure, so increment its count, move it up the list, nothing else happens. Then F comes along, and okay, we just increment. So, it's very straightforward. Now, this algorithm will give you, so what you see here is, well, both the things, how they move, right, and which one has changed. And red basically means you had a renaming operation. So this pi went over here, this one stays down there. Okay, so this sounds like a crazy algorithm to use for finding heavy hitters. After all, we are, sometimes putting items into our data structure that might not have had only a single count. And we're giving them a ridiculously high count. So let's say F came in here and now it has a count of 3 and it may have only occurred once overall. So why does it work? So, and by the way, this is really trivial to implement. Trivial if you find the right tools. So there's something called a bimap in Boost. And it basically is a list that you can sort by two indices. You want to sort it by one index such that you can do a quick lookup. You want to sort it by another index, namely the counts, in order to find out which is the smallest guy to event. Okay. So now this algorithm has amazingly strong bound guarantees. The first guarantee is that the count that I'm observing is an upper bound on the actual count, and even more so that it's upper bounded by the actual count plus total number of observed symbols divided by number of bins. Okay? That sounds reasonable. Now, turns out the bound is even tighter. It's the smallest counter in my list that upper bounds the error for everybody. In fact, you can do even better than that. The upper bound is going to be the actual count plus, so this is basically the tail of my observations divided by where I cut off, so I'll show you that in a moment. Let's say these are my counts. If I have a subfloor distribution, basically there's very little that's happening over here. And then F1k is, let's say I pick k here, is basically that entire mass. So in other words, the heavy hitters that I have in my set don't really affect the accuracy, which is great. It's really only those guys here. Furthermore, this is as good as it gets. And if I have an estimated position I, then this really majorizes the i's true count. And as said, if I insert more key items, then under reasonable conditions, like if the item was already in the set, it doesn't increase the approximation error. It may actually reduce it. It'll reduce it as follows. Suppose I have some item which is actually turns out to be frequent and is in the list in the end, but it dropped out before and then came back. If I see a lot more of those items beforehand, before it dropped out, it may not drop out and just stay on. So this is a really ingenious algorithm by Metawali, Agarwal, and Al-Abadi. And so they went and compared it to all sorts of other algorithms on lots of distributions, and it just works really beautifully. Okay. So now we're going to actually prove this thing. This is a special case of a larger family of stable algorithms and so on. So there's a paper by Birindi, Indik, Strauss, and Cormode, or some permutation of these authors, where they prove it for a much larger, more general family of algorithms. But these are actually the ones that you're really interested in. You don't really care that much about the rest. So, first thing is we'll get a simple error bound. So at each step, of course, the counter goes up by 1. That we know. And since we have k bins, so therefore, if I have n instances, at the end, the total sum over all the instances is n. So if I have k bins, the smallest bin has to be less equal than n over k. Right? So that gives me the upper bound on the error. And as follows, so at any time, when I go and insert an item into my data structure, if I've never seen the item before, the error that I'm going to make is at most n over k at that time. If it stays in the data structure and just keeps on getting incremented, the error isn't going to be any larger, so n over k is already done. If I have an instance that goes into the data structure, is kicked out, and comes back again, the only thing that could have happened in that case is, since it was the smallest counter, that counter went up in the meantime. And then it came back. Now, since it went up, okay, sure, the inaccuracy increased a little bit, but it's still less equal than n over k. So therefore, the error is always less equal than n over k. Furthermore, the same argument that I told you right now also shows that it's an upper bound on the actual counts. You may not really detect everything, but whatever you detect is going to be upper bounded by the counts that you see. Okay. Now, by the reason that I just told you, it's actually the smallest element in that list that really drives everything. Because that's basically the error that worst case you're going to make. So that's claim number 2. Claim number 6, observing an element that's already in the list doesn't increase the error. Well, that's exactly what we already had before, because that counter just goes up, nothing changes, and so this is done. So we've proven claims 1, 2, and 6. Okay, let's prove that the rate is optimal. And so the claim is basically any algorithm that tracks at most k counters and doesn't do anything else. You can have, whatever data structure for those k counters, but it's not allowed to do anything else. Will have at most the same order of error. Well, what we do is we basically feed this algorithm 2 different sequences. And these sequences are exactly the same up to the last symbol. And the only difference is that the last symbol in one case, this A was never observed before, and we assume that B is not being tracked. We can always pick that. We can always make its frequency order of n over k, by just picking a distribution that's essentially even. So there always must be one symbol that the algorithm gives up on. And then the poor algorithm doesn't know, whether we're in the case A or B. So now anything that it does, if it outputs 0, it's screwed here. If it outputs n over k, it's screwed there. And so it might output something that's in between n over k and 0, so n over 2k, which still means we have order n over k error. And that proves the lower bound. We've basically constructed a maximally evil sequence which will screw the algorithm. And that gives us the lower bound. Okay. And then, we can fill several pages of proof with the more general case where you have basically a generic family of algorithms that behave like a space saver. Okay. Now this is cute. Any item with count in x larger than the smallest count must be in the array. So assume that it's not actually in the array at any time. Well, it must have occurred at least once at the last time, right? At that time, we know that the count, if we were to stop the algorithm at that time, would have been its actual count plus, some error, which is larger than the smallest element that we saw in the end. But since it was inserted as the smallest element at the time, we have a contradiction. So in other words, the smallest number in our data structure also gives us a cutoff for what we definitely would have had to observe. It means, we could have some other instances in our data structure that we missed, that shouldn't be there. But again, for those, we know that the error is less than, the smallest element. So if you think about it, let's say this is the smallest element, then we know anything in our true sequence that's greater or equal than the smallest element is there. That tells us, in terms of false negatives, that we can't be too bad. Furthermore, anything that's above that threshold definitely needs to be there. Basically twice the threshold. Because that's an upper bound on our error. So, a single element here might be there without any reason to be there, just because, it got inserted last and it benefited from all the counts that it got before. But if it's more than twice that, it definitely deserves being there. Now, next one is that the count at position I actually majorizes the i's frequency. Because basically what we do is we have our entire distribution and it's squished together such that it's, squished onto k elements. We chop off the entire tail and redistribute it among the rest. That's really what this sketch does. Okay, let's say if the item is not in the array, but then the smallest element in the list must be larger, so we have a contradiction, so reasoning up claim number 7 refutes that. Let's say the item is at position I, well then it's trivial because what we observe is an upper bound. If it's higher up on the list, well, sorry, if it's lower on the list, then, well, since we have a sorted list, we know that at position I it would have to be even higher, so it holds as well. This is the only tricky part. Let's say it's lower on the, it's higher on the list, right? So this item here that actually should have belonged to position 4 may sit at that position. How do we guarantee that this counter here is still larger than the true count of this guy? Well, you get that as follows. Well, since it jumped forward, there must be another element that's actually higher ranking than I and is further behind. It has to be, because I mean you can't have everybody move up, somebody has to move down as well if you reorder the list. And that guy has to be at or below position I, and since it has a higher count, we are safe. That's basically the argument. Now for the last part, this is really tight bound. So here I'm not really taking the entire data structure, but I'm just looking at, up to position k. And so what you know, of course, is that, since the sum over the last n minus k items is an upper bound, so it is a lower bound on the actual counters, I also know what my residual sum has to be. And that's basically the proof. Okay, so that's the space saver sketch, and it's an extremely versatile sketch. Let's just recap briefly how the algorithm works. Basically, you have this list, pick the smallest guy, insert and possibly rename. Otherwise, just increment the counters. Coding this up is, if you use the boost by map, maybe 10 lines of code. If you need to build up a doubly indexed data structure yourself, it's for a few more lines. Okay. There's a lot more sketches that behave almost the same way as lossy counting. So that's basically, it just runs space saver but with a different threshold. So rather than running the algorithm at a given level of space, you run it at a given level of accuracy. So your list may actually shrink or grow over time. And frequent, which basically keeps the k counters, but whenever we see a new item, it decrements all the counters by 1 until we have space again. That actually turns out not to work quite so well in practice, but it also gives you a lower bound. Now, a few interesting research questions in this context. One is, I want to be able to generate sketches in a distributed fashion. And these are open research questions, some of them. Some of them we're working on right now and have probably a decent solution. But basically, what you want to make sure is, let's say, each machine gets, a sliver of the entire data stream. And you want to have a setup that is fault tolerant insofar as if one of your machines dies and you want to still, roll out your super duper web analytics tool, if a user comes along and he gets a report saying, well, sorry, we can't actually give you your data because our machine died, you lose that customer for good, and probably another few customers. So you don't want that. You want to improve the accuracy as you get more machines. This is important because if your accuracy is a function of the total number of symbols that you get, and if your service gets very popular, you get more inserts. So what this would do is, basically the absolute error, per observation would go down, which would increase as your service gets more popular, and that's definitely something you want to avoid. So you want your sketch to become as accurate as possible and scale nicely with the number of machines. And you might want to do compression. Say I have a time series and I'm most interested in how many viewers I saw recently, as opposed to viewers that maybe came to my site a year ago. And maybe I care about combinations of frequent items. So there's a lot more that you can do in this context. Any questions about space saving before we move on to very different statistics? None? Okay, good. Okay, Bloom filters. Who's heard of Bloom filters before? Okay. This is one of those amazingly useful data structures. It's one of those things you really should know about, and if you ever have to code stuff up, you will probably need one of those eventually. So it's very beautiful. But so what we're going to do now is we're going to look for, I want to know whether I've seen an item, and I want to get, a high probability statement for this item. So it's a little bit like the F0 problem, except that I'm willing to tolerate some false positives. I don't necessarily need counts, just know that I've seen it. And I want to be able to, or I might want to get, frequency of the items, but I don't want to store the actual labels. And I want to really be able to get such statistics for all the items, not just the heavy hitters. Or I might want to be able to aggregate. Let's say I have two machines and they compute some statistic and I want to be able to merge it quickly. I want to be able to do turnstile. In other words, I might have a lot of items at some point and they disappear again. For instance, I might want to have a good estimate of all users who are logged in and are using my service. So I might not necessarily care about being able to get an accurate number, but I want to have a system working that even after a year, the errors don't build up. So that's what I mean with turnstile. And so there are three algorithms that we're going to look at. One is Bloom filters, the other one is count min sketches, and the last one is an extension of count min sketches called counter grades. So the last one is going to be, I'll just give you the very brief gist of the idea. For the other two, we'll go through it in a fair amount of detail. So here's a simple definition of what a Bloom filter does. We take a bit array, B, of length n. So these are individual bits. And for an insert operation, what I do is I compute hash of it. Let's say insert x. I compute hash of x and I. For I is, in this case, I picked three guys, okay. This one, and that one here. And I set those bits to 1 if they are not already 1. And if I query, I check whether all the bits that correspond to x are set to 1. Okay. So you can clearly see that if I inserted x, query of x will return true. It must return true because if I set a bit to 1, it will stay 1. However, I might get some false positives. False positives occur if I hit by accident, k random bins, if I have a replication of k, that just happen to be set to 1. And so what you want to be able to do is you want to be able to control the number of bits that by accident just happen to get set to 1 if you look for them. And so I'll give you a very simple back of the envelope reasoning for that, and then you can actually look up more detailed things, for instance in the Mitzenmacher book or the Broder and Mitzenmacher review paper. So here's how the algorithm works. So bit array of length n, we insert, set all the bits, and for query we run true if only everything is true. Now obviously you're not going to get any false negatives. Now in order to find out about the false positives, let's do a little bit of reasoning. The probability that some random bit is set to 1 is just 1 minus, and here's the probability that it remains 0. So 1 over n, if I have n bits, is the probability that a random bit will be set to 1. So 1 minus 1 over n is the probability that it will stay 0. And I raise that to the power of mk, because I have m inserts and I have a replication of k. So my Bloom filter, m times k times, picks a random bit and sets it to 1 from the viewpoint of, an arbitrary bit here. Now, this is approximately 1 minus e to the minus mk over n. Now, likewise, the probability of a false positive, and let's assume that things are approximately independent, is, well, I need to compute the probability that all those bits are set to 1, which is, this probability here raised to the power of k. So that is actually pretty close to what the true probabilities are. So now let's see what it actually means in practice. Let's go and minimize k to minimize the minimize over k to minimize the false positive rate. So I take the derivative of this beast, and I get something that, interestingly, can express throughout as fractions of mk over n. Everything else goes away. So I need to set it to 0. And so this vanishes. You can check it if I pick mk over n to be log 2. So what you see from that is actually a whole bunch of interesting dependencies, such as k being n over m log 2. Furthermore, you see that m and n should be of the same order, which makes sense. The more items I get, the more bits I will need to allocate. But it also tells me that the number of bits is not going to grow superlinearly with the number of items that I'm going to see. That's good news. I mean, I can't expect to be able to store with a given accuracy the data in sublinear number of bits. Because, taking things to the limit, I could store, the ratio between bits that I need and items that I store with a given accuracy would diverge, which means I can squeeze arbitrary number of informations in arbitrarily much smaller number of bits, which clearly makes no sense from information theory. So that's why you really need linear scaling. And, okay, so if you pick that, you can get a good number for your Bloom filter. Now, it also gives you a good idea of the fill ratio. Generally, k is something that you would pick around 3, maybe 4. And basically what you do is you can check that, plugging this back in, you get a false positive rate of 2 to the minus k. So 1 over 16th is not so bad, depending on the application. And so there's a lot more detailed analysis, and the link is in the slides. And you can also show that there's a lower bound for the Bloom filter, and you're within small constants of peak efficiency. There are fancier extensions which are more efficient, but given the amazing simplicity of the filter, I wouldn't bother. Okay, here's a couple of really cool things you can do with the Bloom filter. First of all, you can take unions of sets. That's very easy. You have one subset streaming into the first Bloom filter, one subset streaming into another Bloom filter, possibly on different machines. So these are two Bloom filters here that I get. And I just take the OR, not the XOR, but the OR of those two. And that gives me the Bloom filter of the union of the sets. It's very straightforward. I can also therefore, aggregate in terms of time. So you could have, for instance, intervals of length 1 minute, and at some point you don't have quite that much space, so you compress them into intervals of length 2 or 4 and so on. And these are very simple bitmap operations, so your computer is going to be amazingly fast at it. So, for the price that it costs you to store, maybe a floating point number, as a double, you can store 64 of those twitters. The reason why it's amazingly efficient is because it never needs to store the actual item ID. So you're using all your memory for data as opposed to for any indexing structure. This idea will come back over and over again, both in terms of the count-min sketch, and then much later in terms of hash kernels for linear classifiers. Yep?
So what happens if we need to remove something?
You're screwed. So, if you want to remove things from this filter, no chance. Okay, there are variants of this which let you do this. And one of the variants is going to be exactly this count-min sketch. So this is why I explained the Bloom filter first. It's usually not really that much discussed in the context of data streams, but I think it's a very beautiful precursor to the count-min sketch, so that's why I'm showing it to you. Now, you can do other things with it. You can, for instance, do set intersection. You could, for instance, compute inner products between those two Bloom filters, and that will give you a good idea of, the inner product between two sets. The good thing is, well, of course, if I just perform an AND, I don't get any false negatives. But I might get more false positives because, all those guys that were randomly selected and still happen to be dangling around, they will worsen the estimate. That's not good. But I can also, use the number of bits to estimate the size of this union or intersection. And, that's just very basic reasoning. The probability that the bit is set to 1 is, of course, given by the probability that the bit is set to 1, given that, something in S1 was there to set it, plus the probability that something in S2 was there to set it, minus the probability that, it was in S1 and S2. Because otherwise we overcount. It's just a standard Venn diagram, right? And so then you can just, work out those probabilities. You get that expression for the probability that the bit is set. You then, perform this operation, count the number of bits, and based on that you can both estimate the number of elements in the union and also in the intersection. And by and large what it means is that the number of bits that are jointly in both Bloom filters or just in a single one will uniquely will be a good proxy for how many elements you have in the sets. Modulo the fill ratio and all that, so that's where the exponentials come from, but back of the envelope this is going to be a good estimate. Now, removal, right? So plain Bloom filter doesn't actually allow you to do this. So there's something called a counting Bloom filter, and basically here's what it does. If we see an element, so plain Bloom filter just if it's there, if it's not, if we see an element, we just set all those bits to 1, but we don't really know whether these were set before, and for the query we return true if all those bits are set to 1. Now, for the counting Bloom filter, I'm going to do the following thing. I'm going to replace those bits by small counters, like 2-3 bit long counters, so they're tiny. And so the first thing is I return true for all i's for which, if for all i's, those counters are greater than 0. I don't look at the actual value, I just check whether they're greater than 0. Now, for insert, and this is why I had to explain the query before I explain the insert, I check whether it's already in my data structure. If it's already in my data structure, I don't do anything. If it's not in my data structure yet, then I go and increment all the corresponding counts by 1. And then to remove, well, I first check that actually the element is still in the set. And then, if it is, then I go and decrement all the corresponding counts by 1. Now, that's not quite safe, right? Because you could still get collisions and, something gets overcounted and you get a false positive and so on. So you still need to deal with false positives, which, let's say I have a false positive for some item and I then decide to decrement it even though I never saw it in the first place, and that will then shred a lot of the other counters. So you need to be a bit more careful. But conceptually, that's all that happens. Okay. Now, I'm going to conclude with a count min sketch. And now that you understood the Bloom filter, this is going to be very easy. Any questions on the Bloom filter before we go to the count min sketch? Okay. So, here's the algorithm. It looks exactly the same, except that now we have one row for each hash function. And so for insert, so basically these are now all integer or whatever counters. I increment all the bins by 1. So unlike before in the counting Bloom filter where I checked whether things are going one way or another, here I just increment. And for query, since I know that now each of those bins here has to be an upper bound on my counts, I return the minimum of the counts. Yes. Are there any questions? So I said this is really like a Bloom filter but with counters. Now the amazingly cool guarantees are that in the approximation error is going to be bounded by, from below by the actual count. This is the count that I'm estimating. Bounded from below by the true count, and bounded from above by epsilon times total number of inserts that I have if I use e over epsilon many bins with high probability e to the minus d, 1 minus e to the minus d. Now, this is actually quite astonishing because if you think about, for instance, your homework, we saw that, well, with Höfting, we got the 1 over square root sample size rate, right? So we basically get that, m would grow quadratically with the accuracy. And we saw something similar before in the AMS sketch where we had the, 1 over epsilon squared accuracy, 1 over epsilon squared as a scaling factor for the number of bits that were needed. Whereas this one here has a 1 over epsilon. It's one of those rare cases where it works. It works because we only deal with non-negative numbers. There is a related sketch, the count sketch, rather than count min, which takes the median rather than the min, and that has the 1 over square root sample size accuracy. But it tolerates both positive and negative counts. Mind you, this allows for increments and decrements, and you could at any time of the algorithm before you query it have negative counts as long as you come back to 0